Hello, and welcome to Lesson 6 of the Fly to Learn curriculum for X-Plane. Today we're going to be talking about flight stability. We'll start with coming up with a definition for stability, and then exploring roll and yaw and pitch stability. We will also be discussing center of gravity and torque, as well as performing test flights to learn about the relationship between center of gravity and elevator deflection. So what is stability? Stability describes the tendency of an airplane to return to its original condition after a disturbance. For example, if a gust of wind pitches the airplane up, a stable airplane will react by pitching down. If the plane is unstable, the plane will continue to pitch up instead of returning to its original condition. Let's go ahead and think about this in a different way. Why does an arrow have feathers on the end? The head of the arrow is heavy and sharp and does the damage. What do the feathers do? Shoot an arrow without any feathers, and very quickly you'll see why the arrows are important. The arrow will start to travel sideways and out of control because any disturbance, like wind or rain, will cause the arrow to change direction. Add feathers and the arrow flies straight. This is because the feathers dampen the effects of any disturbance, helping the arrow fly straight and adding stability. The feathers give the arrow stability by keeping the tail in the back. The tail of the airplane acts like the feathers on an arrow. The horizontal and vertical stabilizers give the plane stability. What if the pilot had worked all day before embarking on a late-night flight, and it was a stormy night, and the pilot was tired? The point of stability is to reduce the pilot's workload and make it easier to fly the aircraft. The pilot wants to be able to look down at a map or let go of the controls for a second to adjust the microphone without the plane trying to roll inverted due to a gust of wind or bump of turbulence. Engineers actually design stability into the aircraft itself. They recognize that no amount of pilot control can overcome an inherently unstable airplane. We will look at two important examples of ways we can increase the stability of an airplane. The first is roll and yaw stability. The second is pitch stability. Many airplanes incorporate a dihedral angle in the wings. Take a look at the wings to the right. Notice that the wings are higher at the tips than where they join the fuselage. These upward angles are examples of dihedrals. A dihedral helps to keep a plane's wings level. For example, a gust of wind causes a plane to roll, dropping the left wing down and raising the right wing up. Dihedral causes the lower wing to rise and the higher wing to sink, restoring stability to the flight path. Imagine the airplane as a teeter-totter with the nose at one end and the tail at the other. The fulcrum, or balancing point of our airplane teeter-totter, is the wing. The distance between the tail and the wing can be thought of as a lever arm that acts like a teeter-totter. We can control the pitch of the airplane by varying the amount of force applied to the tail. In physics, the application of force to rotate an object about a fulcrum is called torque. Remember that you can control pitch using the elevator, the part of the horizontal tail section that moves up or down. We can also increase pitch by adding a force, like weight, to the end of the tail. This newly added force, multiplied by the distance from the end of the tail to the wing, causes the nose to pitch up. We need the plane to be stable, so we locate the center of gravity in front of the wing and put the tail behind the wing. The center of gravity pushes down, which pitches the nose down, and the tail pushes down, which holds the nose up. making the plane stable. Let's go ahead and take a look at these forces in action. We're going to go through quick flight setup and start out in the air at final approach. Go to File, Quick Flight Setup, and ensure you're in the Seattle-Tacoma Airport, KSEA, with the Cessna, flying during the day with clear weather. We want to start in the air, so go to Location, select Global Airport, and from runway 16, the final approach from 3 nautical miles. Press P to pause. Press Shift 8 to see behind your plane. We're going to turn on the lift vectors to see if we can observe how our plane stabilizes when we start to dive. By hitting Command or Control M once, you can turn on the lift vectors. Additionally, you can go into View. Additionally, you can try Special and then clicking Show Flight Model. Click to reveal your navigation. Click to reveal your navigation box and press P to unpause. Climb in the plane and then dive. Do this several times, comparing what is happening with the lift vectors for both the wings and the tail. Pausing here, we can see that as the lift vectors increase during the dive, we see the lift vectors opposite on the back of our tail, keeping the plane stable. Here, the tail is acting to keep our plane stable. When you're finished, make sure to hit Control or Command M to cycle through the flight models to turn off those lift vectors. Go to File, Quick Flight Setup, and ensure you're in the Seattle-Tacoma Airport, KSEA, with the Cessna, flying during the day with clear weather. We want to start in the air, so go to Location, select Global Airport, and from runway 16, the final approach from 3 nautical miles. Press P to pause. Press Shift 8 to see behind your plane. We're going to turn on the lift vectors to see if we can observe how our plane stabilizes when we start to dive. By hitting Command or Control M once, you can turn on the lift vectors. Additionally, you can try Special and then clicking Show Flight Model. Click to reveal your navigation box and press P to unpause. Climb in the plane and then dive. Do this several times, comparing what is happening with the lift vectors for both the wings and the tail. Pausing here, we can see that as the lift vectors increase during the dive, we see the lift vectors opposite on the back of our tail. Here, the tail is acting to keep our plane stable. When you're finished, make sure to hit Control or Command M to cycle through the flight models to turn off those lift vectors. Need more proof that load and balance are important when flying an airplane? According to a newspaper article from the British newspaper The Telegraph, a small airplane crashed in Africa when a crocodile got loose on board the plane. It seems that the animal was smuggled on board in someone's luggage, and when it got loose, all the passengers fled to the front of the plane. This shifted all of the weight of the plane up into the front. No matter how hard the pilot worked to try to put the plane back into control, the plane pitched downwards and crashed. Luckily, this is a very rare incident. On every flight, pilots make sure that the plane is loaded and balanced properly, with all items properly secured. As we said earlier, torque is the application of force to rotate an object about a fulcrum. To better understand how torque impacts airplanes, let's take a closer look at a teeter-totter. In this example, two frogs are sitting on a teeter-totter. One is larger, sitting closer to the fulcrum or balancing point. One is smaller, sitting further from the fulcrum. Let's calculate the torque, also called the moment, for each frog. The frog on the left weighs 5 pounds and is sitting 2 feet from the fulcrum. This frog produces 10 foot-pounds of torque. 5 pounds times 2 feet. Take a moment and try and calculate the torque or moment of the frog on the right. The frog on the right weighs 10 pounds and is 1 foot from the fulcrum. Its torque is 10 pounds times 1 foot, 10 foot-pounds. So both frogs are producing the same amount of torque. The larger frog is closer to the fulcrum, while the smaller frog is further away. They produce equal torque, and so are balanced on the teeter-totter. How far away would a 2-pound frog need to be to produce 10 feet-pounds of torque? What about a 20-pound frog? To solve these problems, simply plug in for the missing distance. 2 pounds times how many feet will equal 10 foot-pounds. That's the same as y equals 10 foot-pounds divided by 2 pounds, which results in 5 feet. A 2-pound frog would need to be 5 feet away to produce 10 foot-pounds of torque. On your own, go through the example for the 20-pound frog. Another frog is sitting 2.5 feet away from the fulcrum. What is the weight of this frog if she is producing 10 foot-pounds of torque? Solve this problem very similar to how you solved the previous, except this time, the weight is the variable. x pounds times 2.5 feet equals 10 foot-pounds. X equals 4 pounds. So let's shift back to planes. We can think about the plane similar to these frogs on a seesaw. The center of gravity for the entire plane is much closer to the nose. This nose of our plane is going to be heavier than the tail. While the tail is lighter, it's also longer, and so the tail itself is further from our balancing point, which is the wing. In reality, there are several moment arms at work here in the airplane, but for our purposes, we are going to simplify the situation and assume that two lever or moment arms are impacting pitch stability. The distance from the wing to the center of gravity is the COG moment arm, which stands for center of gravity moment arm. COG moment arm multiplied by the airplane's weight will give us the COG torque, or COG moment. The COG moment always tries to rotate the aircraft's nose down. The tail must counteract the COG moment to hold the nose up. The distance from the wing to the tail is the tail moment arm. The tail moment arm multiplied by the force generated by negative lift will give us the tail torque, or tail moment. The center of gravity moment equals the tail moment when the nose is not pitching up or down. This is when the plane is in equilibrium. If the plane is pitching up, which is greater, the COG moment or the tail moment? If the plane is pitching up, the tail moment is greater. If the plane is pitching down, logically, you should conclude then that the COG moment is greater. Let's investigate how adjusting the COG of the plane affects elevator deflection. Start with quick flight setup to ensure you're in the Seattle-Tacoma Airport with the Cessna flying during the day with clear weather. We want to start in the air, so go to Location, select Global Airport, and runway 16 with 3 nautical mile final approach. We also want to be gathering data during this flight. So go to Settings, Data Input and Output, and we're going to be collecting information on payload weights and center of gravity, as well as elevators. Lastly, we want to change both the center of gravity as well as the payload. So select Aircraft, Weight and Fuel, and move center of gravity all the way to the left and payload weight all the way to the right. We're going to put the plane into level flight and check our elevator deflection. Then we're going to shift the center of gravity all the way in the other direction and do the same. Start by putting your plane into level flight. Note this will feel different because the changes we made to our plane. Use your vertical speed indicator to determine when you're no longer moving up or down. Once you're in level flight for 3 seconds, pause and check the deflection of your elevators. Record in your student handbook. Now go back into aircraft and switch your weight and fuel so that your center of gravity is now all the way to the right, 21 inches forward from the default. Leave the payload weight as it is. Bring your plane back into level flight. Again, using the vertical speed indicator to measure when you are no longer moving, climbing up or down. Once you've been in level flight for 3 seconds, pause and record the deflection of your elevators. When finished, be sure to put your X-plane back to its default settings, with your center of gravity 0 from default, and your payload weight at 243. You can also turn off your data input and output.